Hello everybody. Today we will start a new chapter called Gravitation. It is for class 9. Now, let me start by saying that you may have heard this story that Newton was sitting under an apple tree in his backyard and an apple fell on his head. And because of that, he discovered gravity. But let me tell you that this is not a true story. The actual story was that during the time of plague, Newton was with his other friends and his other friends from university, and he was studying at home. He was looking outside the window and he saw an apple fall off the tree. An apple fall off the tree. And then he discovered gravity. So, first of all, let me tell you that what is the meaning of the name of this chapter? Gravitation. So, basically, gravitation is the force of attraction, is the force of attraction between any two objects in this whole universe. Force of attraction between any any two objects in this whole universe. Whole universe. This statement was given by Isaac Newton. So, Newton said that everything in this universe attracts everything, not only celestial bodies, but even I am attracting this laptop, or even I am attracting this pen. But many people didn't believe in Newton because they couldn't see a clear evidence. So Newton wanted to give evidence. He wanted to give a concrete evidence. Hence, rather than giving a definition, he even formulated a new formula. This formula is known as the universal law law of gravitation formula. Gravitation formula. So, what is the formula? The formula is F is equal to G M M divided by R square. I'll describe these terms for you. Now F is the force. F is the force. But the force of what? F is the force of gravity. F is the force of gravity or gravitation. Gravity slash gravitation. G is the universal gravitational constant. I will be discussing this in a few minutes. Universal gravitational constant. M is the bigger mass. Bigger mass. And small m is the smaller mass. R is the distance. You can also write it as d square. Now, and the distance is squared. Now I'll tell you that what are the basic crux of this formula. What is it trying to say? As I told you earlier, that because the definition wasn't enough, Newton made his own formula. And this formula is known as the universal law of gravitation formula. This formula is used to calculate the force of gravity between the two objects. Suppose force of gravity between the two objects. Suppose the earth is attracting the moon. Okay. Now I want to find out that what is the amount of force that the earth is exerting on the moon to keep it in orbit. So I can use this formula to find that how much gravitational force, how much gravitational force the earth is exerting on the moon. Now we'll talk about we'll define the formula. Now the force of gravity, I have defined the force of gravity is equal to gmm divided by r square. Now what is g? I promised you that I'll discuss what is capital G in a few minutes. So g is basically the universal gravitational constant. Capital, one second, capital G. So this is known as the universal gravitational constant. Note, the universal gravitational constant wasn't discovered by Newton. It was discovered by a English scientist named as Henry Cavendish. Now you may be wondering that what is this universal gravitational constant? So Newton, universal gravitational constant. I'll define what is universal gravitational constant. It is the force. It is the force with which an object of unit mass, you can ignore unit, I just meant of any mass but not zero, which is not equal to zero. It is a force is not equal to zero, attracts another another object in another object within a unit distance. So I won't make it extremely complicated for you guys. Let me tell, because this chapter is for class 9. This is for class 9. That's why we only have to revise this definition. We don't have to do anything else, because the derivation of the universal gravitational constant and more complex things will be done in class 11. The universal gravitational constant will be derived in class 11th. So you may be thinking that how did Henry Cavendish measure the universal gravitational constant? Because so Henry Cavendish used a torsion balance. A torsion balance. Yes. So I'll draw torsion balance for you. This is basically what a torsion balance looks like. So these are two weights weighing exactly 1 kg, and these are lead blocks, and this is one thin copper wire, and this is hanging to the ceiling. This is the ceiling of the room. So this is what a torsion balance looks like, on which Henry Cavendish measured the universal gravitational constant. Now the value of the universal gravitational constant is 6.7 into 10 to the power minus 11. Now what I mean by 10 to the power minus 11, because the force is so less, it will come in 0.1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the amount of force. Hence, it is written in scientific notation to make it more convenient for us to read, because this is an extremely long and extremely complex value. Hence, it is written in a much easier way. Now, you may be thinking that I have told you guys the value, but what are the units? What is the SI unit of the universal gravitational constant? Now, there is actually no need to define, I don't need to give you the exact units. You can derive them easily with the formula. You may pause the video and try it on your own. Let me give you a hint. It is basic algebra, and you have to use this universal law of gravitation's formula. Okay. Now I'll start by deriving the units of the universal gravitational constant. As I'd given you a hint, we have to use the formula of the universal gravitational law. So it is F is equal to G divided by R square. So G is the universal gravitational constant. Now with basic algebra, we can shift R square to this side. So we can do F R square is equal to G M, right? Now we can shift M and M to the other side to exclude G, which gives me F R square divided by M is equal to G. So this is the formula of G. Now with the formula only, we can easily derive the units. So what is the SI unit of force? The SI unit of force is Newton. The SI unit of distance, meter. That's why we'll write meter square divided by SI unit of mass. This is kg squared. So hence we easily derive the SI units, and they are Newton meter square divided by kg square. So this is the SI unit of the universal law of a universal gravitational constant. Okay, now I'll continue to now I'll tell you that what did Newton state about this formula. Now by state I mean that Newton's explanation, what theory he gave about the formula. He said he said one second, sorry for the interruption. The force of gravity is directly proportional to the product of masses and inversely proportional to the square of the distance. Now I think the same thing, that this definition is extremely complex and it makes no sense. That's why I'll make a few illustrations so that you can visualize that what is the definition trying to say. One second, yes, this is what it is. Fine. So the force of gravity. Now let's consider two balls. This is ball 1 that has M, capital M. That means it has a bigger mass. It is more heavier. And this is ball 2. Ball 2. And this has a smaller mass. That means it is lighter. Now, the force of gravity between these two balls. So the force of gravity between these two balls is directly proportional. Directly proportional means that if the force increases, one second, by directly proportional I mean if the force increases, the mass also increases. And if the force decreases, the mass also decreases. Or it can even be the other way around. If the product of the mass increases, the force increases. It's That's what it means. It is directly proportional to the product of the masses. By product I mean m1 into m2. Now this 1 and 2 is just to tell that it is ball 1 and ball 2. So m1 into m1 into m2 is directly proportional. This is the sign of proportionality, directly proportional to the force of gravity. Now here G is to clarify that this is the force of gravity. Gravity. Okay. Directly proportional to the product of the masses. We are done with this part of the definition. Okay. So I'll mark this as green because we are done with it. And it is inversely proportional to the square of the distance. One second. Distance. Now, by inversely proportional, I mean if this distance increases, the force decreases. I'll give you an example of magnets. There is this magnet 1 and magnet 2. If I keep these small magnets 1 kilometer apart, will they even move? Obviously, they won't, because the force of magnetic force is not strong enough. The same thing is being the same thing is being conveyed here. Now, if I keep the magnets in a distance of suppose 1 centimeter, so they'll obviously attract and they'll join together. Yes or no? Because the distance has decreased. This only is the same case with gravity. Now suppose there are two objects, ball 1, this is ball 1 and this is ball 2. Now if they are kept 2 kilometers apart, they won't come together, or the force won't the force will be too less. And now if I bring them close as 1 millimeter, the force will be comparatively higher. It won't be high, but it will be comparatively higher. So this is what is being tried. This is what Newton was trying to convey to the square of the distance. And we are done with the definition. Now you may be thinking that I have told you. Now you may be thinking I have told you force is proportional to product of masses. One second, number one, and force is inversely proportional to the square of the distance. But how did we get this formula? How did we get this formula? Question mark. How did we get it? So this is an extremely easy question. How did we get it? Now to derive any equation, we can multiply this and we come out with the product as F is proportional to mm divided by d square. Now still we have this proportionality sign. It is irritating us a lot. Now we need to get the equality sign. So now whenever we have to get an equality sign, we need a constant of proportionality. It is represented as k. I don't know why is it represented as k. It should be represented as c. But scientists and mathematicians have said this is the that k is the constant of proportionality. Proportionality. Yes. K is a constant of proportionality. Now to remove this, we need a constant. Pause the video and think, when did I last say the word constant? That's right. I said the constant was big G. 6.7 into 10 to the power minus 11 Newton meter square divided by kg square. This is the constant. Hence we can put G, big G, mm and r square. So this is how we easily derive the formula of universal law of gravitation. Okay, bye for now. I will explain other concepts too in the next videos. Thank you for watching. Please like, share and subscribe to my channel.